Last year I made a video about my first ever electronics project, a granular synthesizer called the Arduino, which I've actually got over here. At the end of that video, I promised I'd be back soon with another project, sequencer this time. So, after spending an entire year in lockdown dealing with multiple failed builds, learning to code, and literal explosions, here it is. The After 8 step is a machine learning enhanced sequencer built using Arduino and Max. It builds off of the typical Baby 8 style of DIY analog sequencers documented by Mark Verboss back in the 90s. Typically, analog sequencers will take several pitch inputs and repeat them infinitely. The secret behind my After 8 step sequencer is the addition of Markov Chains. Markov Chains control how the sequencer moves between steps, meaning I can set the device up to intelligently write its own music inspired by the information I give it. Connecting the analog sensors via an Arduino allows for a tremendous amount of customization in code, meaning the physical system could be adapted to many projects. The After 8 step has two chains. One writes its own melodies generated only from the sequencer's pitches, and the other has probability values that can be manually tweaked to create interesting new patterns. I'm going to go over that in more detail as this video goes on. Traditionally, sequencers are very repetitive. This sounds great in many situations and it's obviously by design, but this looping nature is also a significant limitation if you want to create more evolving song elements. I want to bring the idea of analog sequencers to more modern technology, allowing experimentation with the new possibilities that microcontrollers can bring to music production and sound synthesis. I've created the hardware hoping that it will be useful in multiple situations, meaning that anyone who builds this, me included, isn't stuck with one objectively strange piece of equipment. I wanted this particular implementation of the project to have the ability to be set up and left alone, much like a sequencer, but also address the need for more variation in certain circumstances.
Cat. Cat.
This project uses 16 potentiometers, 16 LEDs, about 20 resistors, an LCD screen, a single rotary encoder, one push button, 4 CD4051B multiplexing chips, a lot of wire, and an Arduino Nano. Much of the programming is done in Arduino, but the more complicated elements are done in a visual programming language called Max. I'm using Max for this because it's a lot quicker to code with. Uni bagged me a free copy, and this is my first coding project. First, I measured out the right size for the holes on the top of the tin. This is super important. In the past I've done this just slightly inaccurately and it's looked pretty bad. I measured the component's diameter using a crochet hook guide. Technically you want a drill bit gauge, but this works for most little parts. I measured everything and then printed out a guide before I drilled in the pilot holes. Got to avoid these pesky measurement errors. I used a step drill bit to widen the pilot holes to the correct size before mounting the pieces. Honestly, I would advise doing the soldering beforehand to more easily isolate the parts from the case when soldering. This first row of potentiometers controls the pitch of the output through the max patch. I've coded the Arduino to read all 8 potentiometers through one input pin using multiplexers, and then sent these sensor values through the Arduino's serial port to max. I've done another video covering that process in a lot more detail, which I will link somewhere in the description. Once the inputs get to max, they're sent through a scale object. This object converts the potentiometer values from 1023 distinct steps to a small selection of MIDI notes. MIDI notes are numbered from 0 to 127, representing every note for almost 9 octaves on a keyboard. I've decided to scale my potentiometers to between 50 and 80, which is a bit of a cheaty way to output notes with each potentiometer turn, as these values can be read as MIDI values by a lot of the objects in Max. I then plug these MIDI values into a col, which is a list or array of values accessible from anywhere within Max. This means that I can access this list from multiple places in the patch without creating a huge mess of virtual wires. This counter object is firing out a loop between 1 and 8 at a specified tempo. These numbers can be used to access the col's potentiometer values, with each number in the loop referring to a MIDI step in the sequence, a sequencer. The easiest way to get sound out of this is to plug these MIDI patches into a MIDI to frequency object, converting them into frequency values. Sending these values directly into an object which creates sine waves, the cycle object, creates a note for each step. I've also gone ahead and tweaked this slightly to use a note out object in place of the cycle. This means that the sequencer can control any MIDI instrument that you have on your computer. The music you hear throughout this video were created by linking up the sequencer to Ableton. Because Max has 2 MIDI outputs, I can use different instruments for the original sequence and the Markov sequence, which is particularly important when using the sequencer live rather than for recording purposes. Making the opening for the LCD screen was kinda hard, mainly because I don't have the right equipment. Using a drill and a pocket knife, I opened up a space about the same size as the screen and then squished the sides of it flat. I could then drill a hole into each corner and mount the screen. I've noticed that different countries have different colour regulations for wiring. Often things will be in American standard, red and black. In England it's blue for ground and brown for power, because if you touch brown, you'll shit yourself. I'm not sure I want to test that one out, but it certainly made me remember the colours. So for every potentiometer here, I'm going to attach a ground wire to one side and a live wire to the other, and do the same to the rotary encoder while I'm there. I attached a 220 ohm resistor to each LED's shorter leg, the negative anode, and I covered this with heat shrink to protect against short circuits, although I kinda regret how I did this as they are far too long. I ended up having to fold them in half in the final box to even get it to shut, which is fine because it works, but in the future I would definitely cut them a lot tighter. Using a lighter like this is also not that efficient, let alone painless, so a hairdryer would have been better. I connected each LED's positive leg to ground and used hot glue to stick them into the casing. This works nicely, it's a trick I stole from Look Mum No Computer, to be honest, and I'm also apparently really messy with it, like what am I even doing there? And then I do all of that again for the second row of LEDs. All of these LEDs are showing which step the sequencer or Markov chain is at. The first row of LEDs play in order, these yellow ones here, demonstrating both the tempo and which potentiometer is related to each step. The second row, the green ones, show which step the Markov chain is playing to provide visual feedback. The LEDs are sent this data from Max very similarly to how Max reads the potentiometer data, but in reverse. I've sent out each step number as an ASCII letter and written code in Arduino which interprets these letters and lights up the LED at the correct step. So on to the second row of potentiometers. These potentiometers are used as the input for the adjustable Markov chain within the Max patch. They're brought into Max identically to the first set, but are then used for an entirely different purpose. I'm using these numbers to provide the Markov chain with a user-controllable probability for moving to each step. By rearranging this data, I can create a transition matrix which doesn't rely on the original sequence. A transition matrix is a web of probabilities that form the basis of how a Markov chain makes its decisions. It looks fairly similar to a flowchart. For example, in the case of a sequencer, the chain follows a linear pattern. Step 1, step 2, step 3. The probability of moving to the next step is effectively 100%. However, if I use a Markov chain to change these probabilities, this web becomes much more complex. What you can see here is a transition matrix using the 3 above steps, but giving them different likelihoods to travel forward, backward, or repeat. These 3 relative likelihoods form the basis of the extra controls that are accessed via the Rotary encoder. I've written the Arduino code for the Rotary encoder to allow saving of 3 distinct values, moving between each setting with a click. When sent through this very complicated looking net in Max, these settings are used to control the likelihood that a step will move forward, backward, or repeat. The potentiometers themselves are used to control each step's individual likelihood of being moved to, which are then added to the setting values and translated into percentages by the Markov chain. Adding these 2 variables together means that you can create all sorts of crazy non-sequences. When I was putting together the first draft of this Max patch, I tried to plug the MIDI notes themselves directly into the Markov object. This is still in the Max patch, but without hardware control. This chain analyzes the 8 MIDI notes and tries to figure out the probabilities between each one and create a transition matrix. This is similar to a technique implemented by David Cope in the 1990s. He manually inputted a variety of note data for all of Bach's musical compositions. The music that came out of the computer was enough to fool an audience into believing it truly was Bach, who was shocked and delighted to be told it had been computer generated. Though this technique works amazingly well when analysing large datasets, such as all of Bach's compositions, I quickly realised that it wasn't applicable to an 8-step sequencer. When each pitch in the sequence was different, the only inference the chain was able to make was a 100% chance of any step moving to the step following. This creates a transition matrix identical to a sequencer, as we discussed a moment ago with this image, meaning that it will just copy the sequencer precisely, the opposite of what I want. One way to deal with this is to just, make sure some of the notes are the same. This, however, takes away from the freedom of expression and still has the distinct feeling of a couple of loops playing in a semi-random order. Another way is to set the Markov Chains order to 0. This means that it won't factor in any of the previous steps when calculating its transition matrix. But this makes it an essentially random sequence using the inputted notes. Again, not really what I wanted. Now I'm going to come in and attach a long signal wire to every potentiometer's center pin and each LED's resistor leg, which will connect to the multiplexing chips. To make the multiplexing board, I've soldered 4 CD4051BE chips to a strip board piece. Unfortunately, I did get one of them upside down, but it still works. It just makes them a bit less intuitive to wire up. I haven't got it in camera actually, but it's important to remember to break the connection between each side of the chip on the strip board. Without doing this, each pin would be bridged to the one opposite it, which would cause a lot of issues. The easiest way to do this is to drill away some of the traces by lightly using a drill bit. Multiplexers are integrated circuits similar to an automated selector switch, which allow a system to read inputs from several sensors in quick succession. Once I got my head around the abbreviations on the datasheet, wiring the multiplexers wasn't too complicated. It's similar to wiring a potentiometer, but using the chip's outputs instead of the Arduino's directly to connect to the central signal pin. The multiplexer's inputs are read sequentially by sending binary code via pins A, B, and C. These codes tell the multiplexer which pins to read, sending 8 values using binary. I spoke about this in my short video series on multiplexing in Arduino and Max that I mentioned earlier. I then connect the multiplexers up to the Arduino, including the ground and power rails. Each of the multiplexers has its own signal pin, but shares the 4 Arduino pins that send the binary messages. This means that I have to connect these shared pins between each multiplexer before attaching them, which is a little fiddly, but doable. I definitely cut most of the wires in this project too long though. I decided to do a quick test, and as you can see, it's not very happy, but we'll get there. Now I'm connecting up the Rotary encoder, which I use to control the extra settings I mentioned earlier. One thing to note about the Rotary encoder is that I found it very tricky to integrate with the multiplexers in Arduino. This was likely due to my lack of coding knowledge, but that, combined with having only 2 interrupt pins on the Arduino Nano, made it difficult to pick up the button press at the correct time. An interrupt pin can be read instantly, interrupting the code loop. Anything happening on these pins takes priority over the rest of the code. This was fine when connecting the encoder's 2 binary outputs, but the button is on a 3rd pin and links to an Arduino pin without interrupt capabilities. This combination led to my inability to find a place in the loop where the value entered doesn't travel between setting 3 and 1. The setting can still be adjusted once you get there, so there are manual workarounds, but I'm still unsure how to entirely correct this without a 3rd interrupt pin. If anyone has any ideas, I would greatly appreciate them. This clicky green button I'm connecting up now will hopefully eventually be set up to start and stop the sequence. Wiring up the LCD screen was pretty complicated, even though I had a breadboard version to reference. I was fairly convinced I did something wrong. I could barely read the output on the screen, so I decided to add a potentiometer to control the brightness. Unfortunately, I connected this in a bit of a panic and did it completely wrong, which resulted in a resistor on the Arduino I was using literally exploding. I thought this might at the least make exciting footage, but you don't see anything. I was really pissed off at this point and left the project alone for a while before coming back to it. At the time, I was convinced I'd used a shoddy Arduino, but looking back, it's almost definitely that wrongly wired potentiometer. A few days later, I came back and ripped the heart out of my attempt at Look Mum No Computer's 8-step Arduino sequencer. His sequencer was a massive inspiration for this project, even though I couldn't actually get it to work, which makes the After 8-step technically my third electronics project. After taking the Arduino out of that and cutting the strip board to a more manageable size, I started transferring over the old one's connections. I really wish that I hadn't removed all of the wires at once, as it meant that I had to go back to my old wiring diagrams and analyse the hardware to try to remember what I'd done. I really need to make more relevant notes. Once I'd painstakingly moved over each wire, I tested it out, and it worked. I admit I am surprised that I managed to sort the problem out, because I felt a bit hopeless when the thing exploded. I think that all in all, this project went better than I expected. The end result is cute, a very thick and heavy boy, and beyond that, it works. When I started this project last year, I expected it to just copy somebody else's schematic, but thanks to a lot of effort, frustration, and support from others, it has turned into a lot more, so yeah, thank you. In her book Hello World, highly recommended, Hannah Fry says, "The real issue is not whether machines can be creative. They can. It is about what counts as art in the first place." I want to take the After 8-step and actually use it in music. First, I need to figure out how to vary the control that the Markov chain has. I intended for the sequencer to make its own choices, but with the artist still able to intervene and fine-tune parameters. What I've ended up with is close to that, but not quite. The Markov chain is either working fully independently using the pitch data or controlled only by the potentiometer values. I really want to create something that is a blend of the two. Artificial intelligence in music is sometimes controversial, but definitely a fascinating topic to me. In the aftermath of the critical backlash to David Cope's back-imitating, musician-defeating electronic music interface, he said, "Back created all of the chords. It's like taking Parmesan cheese and putting it through the grater and then trying to put it back together again. It would still turn out to be Parmesan cheese." Though machines can emulate humans' music, they do need an awful lot of training data to do so. My lovely tutor at university suggested creating transition matrices based on data from popular music. This addresses the issue of the 8-step data being too small for the Markov chain to analyse on its own, and might allow for even greater synergy and easy variation in the music. It does, however, slightly change the outcome once again, pulling it even further away from its 8-step origins. I'm not sure that's a bad thing, and it is something I definitely plan to experiment with in the future. It might take me a while, but I will definitely be posting some more videos on the topic, so if you're interested, subscribe to this strange channel for more updates on what I'm up to. This one took me a really long time, and I'm honestly pretty proud of it, so yeah, thank you. which was a granular synthesizer. Nooping. And sound synthesis. Fuck, I can't say synthesis. Sound synthesis. Synthesis, it's not that hard to say. And sound synthesis. Stop saying synthesis. That's not a word. And sound synthesis. Sound synthesis. Production and sound synthesis. Synthesis.